I'm gonna be honest, I don't really get what I'm about to go over. But I'm gonna try my best. Oh Lord, calculus was a doozy today. We started chain rule for multivariable functions. But in order to explain the formula that I am about to show you all, it's going to require some setup. If we have some multivariable function, we know that the gradient vector is going to be equal to the partial derivative of that function with respect to x, comma, the partial derivative with respect to y of that function. This is going to be really important for the theory that I'm about to lay down. There is a certain equation that our multivariable function needs to fulfill if it is going to be differentiable at a certain point AB. We take the limit as x comma y approaches that point AB of this function. F of x comma y minus the quantity of f of a comma b plus grad f ab dotted with x minus a comma y minus b all over the absolute value of x minus a comma y minus b. And then this is all equal to 0. If the limit as x comma y approaches a comma b of this function equals 0, then we know that our function is differentiable at the point AB. This equation is honestly artificially complicated. I'm dead certain that whoever created it to... I am convinced that whoever created this damn thing did so with the specific intent to intimidate as many college students as possible. Because this thing is just derived from our original definition for a derivative. It is a monstrous mishmash of that definition and our partial derivatives. Notice our gradient vector there. Let's continue by changing this function up a little bit. We are going to introduce two vectors. R is equal to x comma y, and R naught is equal to a comma b. Let's put this function up here in terms of this. This is going to be our new limit. The limit as r approaches r naught of f of r minus the quantity of f of r naught plus grad f of r naught dotted with r minus r naught all over the absolute value of r minus r naught. And you may be like, well, that doesn't seem very different than the past one, and I would say that you're right. It isn't. But this shows us something important. We can put coordinates in terms of vectors. And for this, we're bringing back parameterization. Let's say that we are given a curve, and then after we parameterize that curve, we have this r of t. If we plug this parameterized curve into another function, we can plug in a t and get an x and y value to plug into the function, and then we get a value from the function itself. This setup, where a vector is embedded inside a function, is called a vector-valued function. Now, let's imagine that we want to take the derivative of one of these vector-valued functions. We have a very specific equation for this. The derivative of this vector-valued function is going to be grad r of t dotted with r prime of t. But let's remember that we can plug things in for r of t, where r of t is going to equal some x of t comma y of t. We plug in one t, we get an x and a y value, which means that we can write the derivative of the vector-valued function as this: the derivative of f of x of t comma y of t, meaning that the derivative of this vector-valued function is going to equal the partial derivative of f of x of t comma y of t times x prime of t plus the partial derivative with respect to y of x of t comma y of t times y prime of t, which can be written in one last form. We know that r of t is going to give us some x of t comma y of t, and if we set z equal to f of x comma y, we can write the partial derivative of z with respect to x in Jacobian notation, which is the following: the partial derivative of z with respect to x times dx dt plus the partial derivative of z with respect to y times dy dt. For my own sake here, I am going to do an example. This stuff is so much more complicated than normal chain rule. We're given an equation for z, x squared y plus 3xy to the fourth. We're given an equation for x, sine 2t. And we're given an equation for y, which is cosine t. We're given a certain t, equaling 0. We want to find dz dt at that t. Let's get it started. First is the partial derivative of z with respect to x. When we're differentiating with partial derivatives, we imagine everything except the variable that we are taking the partial derivative with respect to is constant. This is the derivative we're looking for. Next is dx dt. For that, we are literally just going to differentiate x. Simple chain rule trig derivative. Next is the partial derivative of z with respect to y. We use the same strategy that we used with the partial derivative with respect to x, except this time we imagine that everything except y is constant. Simple enough. Now we differentiate y, literally just negative sine t. Let's recall our equation for dz dt, the partial derivative of z with respect to x times dx dt, plus the partial derivative of z with respect to y times dy dt. Using the values we found before, we can just plug those into that equation. Doing that, we get this. The last thing we need to do is plug t into this. But first, we need to remember that x and y don't just mean x and y, because obviously we aren't specified in x and y by the problem. X of 0 and y of 0 are 0 and 1 respectively. Finally, we can plug everything that we know into that equation. We've plugged everything in, now let's just simplify. dz dt at t equals 0 is 6. We're just going to skip straight to physics today, because I was right. We covered exactly what I thought we were going to cover in last night's video. Makes me very glad that I did the homework, because the example problems were literally just pulled from the homework. I don't know if I've mentioned this before, but the homework is optional. It isn't technically graded, but it does provide vital practice for one. So it is pretty much required if one wants to get a decent grade in the class. So on to physics. Last time we talked about dipoles and their properties. It turns out we can connect them. It turns out that we can connect them to capacitors. Here's how. First, a little bit of vocabulary. A dielectric is an insulator that is placed in between the two plates in a capacitor. It being an insulator means that the charge inside of it cannot freely flow, but something else can happen. Let's imagine that these two dotted lines represent the plates of a capacitor. They have a charge density of positive sigma and negative sigma. Now let's imagine that we put some insulating material in between them. Now let's imagine that we put an insulating material in between these two charged plates of the capacitor. What's going to happen in this insulating material? First of all, this insulating material is a dielectric, meaning that charge cannot flow wherever it wants around this thing. But in the molecules making up the dielectric, some cool stuff is going to happen. If we imagine all of the molecules inside this dielectric having poles, those poles are going to flip and orient themselves towards whichever end they are most attracted to. Positives are going to orient towards the negative charge, and negatives are going to orient towards the positive. So despite the dielectric not having charge in and of itself, there is going to be a positive and negative induced charge density. And we already know that there is going to be an electric field between the positive and negative charged plates of the capacitor. This induced charge density is going to create an electric field running in the opposite direction. An induced electric field, if you will. Using this, we can find the total electric field in the capacitor. The total electric field is just going to be E naught minus the electric field induced. Since this is a parallel plate capacitor, we can imagine them as just running up or down. So instead, we can just take the magnitude. And the magnitude of the total electric field is going to be the magnitude of the electric field just due to the capacitor divided by a dielectric constant. If you put a dielectric inside a capacitor, you are going to lower the electric field in that capacitor. By how much depends on the material. But I don't think we're going to be asked to calculate this constant. It's kind of like specific heat, where we just know that copper has a certain specific heat and a certain state. All dielectrics have their own dielectric constant. But let's take this a little bit further. We can use Gauss's law to find the electric field due to the capacitor, Q over A epsilon naught, which is simply going to equal the original charge density divided by epsilon naught, because Q divided by A is charge density. We can do the same thing for the induced electric field. Qi over A epsilon naught is equal to sigma induced over epsilon naught. Using Gauss's law, we know that there is a direct correlation between the charge density and the electric field produced. But there's also something that we know about dielectrics in general. There is a correlation depending on the dielectric constant between the charge density of the capacitor and the induced charge density. The induced charge density is just going to be the quantity of 1 minus 1 over k times the normal charge density. As we can see here, the induced charge density is always going to be less than the normal charge density. And that the larger your dielectric constant is, the closer that you are going to get to perfectly matching induced charge density with regular charge density. As k approaches infinity, this part approaches 0, meaning that the induced charge density would simply be 1 times sigma, meaning that sigma induced would just equal sigma. But these are really just the internal workings of dielectrics within capacitors. This is what is happening inside the dielectric itself. But do these dielectrics affect how the capacitor functions as a whole? You know that they wouldn't teach it to us if it didn't. Firstly, we know that capacitance is equal to charge over voltage. And we know that voltage is going to be equal to the electric field times the distance. And we know that the electric field due to the capacitor is simply going to be sigma over k times epsilon naught, which can be translated into q over k epsilon naught a. Let's find the voltage by multiplying our electric field times distance. Now we have our voltage. Let's plug it into our equation for capacitance and see what happens. Our capacitance is going to be equal to q times k epsilon naught a over qd. The q's cancel out, leaving us with k epsilon naught a divided by d, which, if we notice and be a little bit sneaky, leaves this part being equal to capacitance, or at least the capacitance without the dielectric, meaning that the capacitance of a capacitor with a dielectric is equal to the capacitance of the capacitor without the dielectric multiplied by the dielectric constant. Isn't that cool? Meaning that the stronger your dielectric is, the weaker your electric field inside the capacitor is going to be, but the stronger the actual capacitance is going to be. It's an inverse relationship. If we imagine the same logic and train of thought there, we can also find the voltage inside a capacitor with the dielectric. We know that the voltage is going to be the electric field times the distance, and we know that the electric field with a dielectric is weakened, meaning that the voltage with a dielectric is also going to be lowered, and be equal to the original voltage divided by the dielectric constant. We start resistance next. Not going to cover that tonight, though. We got the most basic of basic introductions. Plus, we had a sub today, so I wouldn't be surprised if the professor went a little bit more over dielectrics tomorrow. Actually, we don't have lecture. Oh my lord, we don't have lecture on Friday. Oh lord, this week's homework is going to be awful. So, quick update. It's been a hot minute. I know I said yesterday that today I was going to go over examples of liberalism and civic republicanism. My god, is it raining out there? No, it isn't. Just the sprinkler system. I should have known, California being a stereotypical drought haven. My plan was to check with the slides that were posted online for that, and after updating my MacBook to the new OS, my Microsoft Office account has gone offline, and I have no idea how to redeem my purchase again. So for the time being, I do not have access to Microsoft Word, Microsoft PowerPoint, Excel, and all the other Office applications. That's going to be a project for me to fix over the weekend. But in preview mode, the new versions of the Office software look sleek. So fate has forced my hand. I'll have to retire surprisingly early tonight. It's only around 10 o'clock right now, which means, hey, you know, more time to edit these videos. So tomorrow will be interesting, because I'm going to get new material for public policy, and I'm going to have material from the calc discussion to cover, and I'm going to look forward to seeing whether I actually get the chain rule. But in the meantime, thank you all so much for watching. See you tomorrow.